In this section, we just want to talk about the sound wave, which is an example of a longitudinal wave. We want to learn about the property of the sound wave first, and then we talk about the standing wave in an organ pipe. Then later on, we talk about the sound intensity and the Doppler effect related to the change in the frequency of the wave. Okay, so we have seen that the sound wave is an example of the longitudinal wave. If we consider this video, so you can see that, okay, so the dot here just represent the molecules of, the medium that the sound wave is traveling to, right? If we consider the red one here, you can see that the red dot, right, it just oscillates to the left and to the right, to the left and to the right. And then if we look at the regions where the molecules stay close to each other, so you can see that the wave, right, it just traveling to the right hand side. Okay, then we can call the regions that the molecules stay close to each other, this part, right, it just called as the compressions. And then the part that the molecule just stay separated to each other is called the rarefactions. So we have the compressions and the rarefaction here for the sound wave traveling in the medium. And also the speed of the sound wave in the substance can be described by these equations. For example, in the solid, right, the speed is equal to the square root of the Young modulus. Okay, you have seen the Young modulus already. Equal to the square root of the Young modulus and then over the density of the solid substance. Also, in the fluid, for example, in the glass, in the gas and in the liquid, right, the speed of the sound waves is equal to the square root of the Bach modulus and then the density of the fluid. Especially in the air, the speed of the sound wave can be described by these equations. So we have the 331.5 and then plus the 0.607 times the temperature in the degrees Celsius. So this will be the temperature in the degrees Celsius. Okay, so one thing that we can see from these equations, so actually just the same as we have talked about the sting wave. So one thing that you can see from this question is that the speed of the sound wave, right, it just depends on the medium. Okay, it just depends on the types of the medium. Okay, so look at this table. For example, the speed of the sound wave in the gas, right, it's just about what? It's just about the 300. Okay, as you can see, the speed of the sound wave in the gas is just about the 300 meter per second. But then the speed of the sound wave in the liquid, right, it's just about 1000 meter per second. So let me just write this form. So it's just about the 300 and about the 1000 meter per second. The speed of the sound wave in the solid, okay, so right now in the solid, it's just about the 5000 meter per second. So that's going to be the order of the magnitude of the speed of the sound wave in the different states of the substance. So now, how about the frequency of the sound wave, right? So you can see that we can have the range from the 1 Hz of the frequency and then to the 1 million Hz of the frequency, depending on the application that we just want to use. The frequency that human can hear, right, it just range from the 20 Hz. Okay, so at this value and this value is just equal to the 20 Hertz, and then until to the 20,000 Hertz. So that's mean the frequency of the sound wave that human can hear, right? But now for the ultrasound, right, the frequency should be greater than the 1000 Hertz. And for the whales, you can hear about 8 Hertz until the 30,000 Hertz, as you can see from this diagram. Okay, so now let's come to an important point. So, okay, from the previous section, we talk about the string wave, right? And then we can describe the string wave using the graph of the displacement y and the position or the time, right, of the string wave. But now in this case, you can see that if we just want to trace the position of the particles, I mean for the sound wave, right, it's going to be quite difficult actually, because if you just look at this simulation, right, you can see that we have lots of the particles in the medium here. Okay, so it's be quite difficult to trace or to measure the displacement of each molecules in the sound wave. So what should we do? Okay, what should we do? So one thing that we can do is we're gonna make the graph between the change in the air pressures. Okay, for example, okay, so now for the first one, right, let's say that if we don't have the sound wave, so it means that the pressure here is going to be equal to the atmospheric pressure. Let me just say it as the ATM. Okay, let me just write down as the ATM. But then if we have the sound wave, right, you can see that we're going to have the part, the regions which is called the compression, right, and we're going to have the region which is called the rarefaction. Okay, so in the regions with the compressions here, the molecules just stay close to each other. So it means that this part, the pressure must be increased, right, from the atmospheric pressure. On the other hand, in the regions which is called the rarefaction, the molecules just stay apart to each other. So it means that in this part, the pressure should be less than the atmospheric pressure here. Okay. So now from this point, then we can just make the plot. Okay, so with this conclusion, wait, let me see, I use the blue one for the compression, the red one for the rarefaction. So I'm going to use the same thing here. The blue one for the compression. Yeah, okay, and the red one for the rarefaction. Okay, so then the graph should look something like this. No, okay, let me just draw it again. Okay, so now for this part, right, we said that the pressure is increased, so it's going to be the top, yeah, right, the crest, and then this part, the pressure just decreased, so it's going to be the trough, and just come back to here. Okay, the pressure just increased, it's going to be the crest, and etc. Then the graph should look just like yep, better, I guess. Yeah, the graph should look just like this. Then I'm gonna make a copy. Oops. Yeah, so it should be something like this. okay, and so on. Okay, so I mean at the rarefaction here the pressure increase, so that's why it's going to be the crest of this graph. And then at the compression, okay, one more time. At the compression, right, the pressure increase, so that's why it's going to be the crest of the graph. And then at the rarefaction the pressure will be decreased, so that's why the change in the pressure must be negative, right? So it's going to be this part. Okay, so then how about the displacement of the air molecules? Okay, how about the displacement of the air molecules here? Okay, so let's see. If we consider the air molecules exactly at the compression at this position, so you're gonna see that, I mean, it's enabling molecule, right? It's gonna move and then compress to this position. So it means that the air molecules at the compression here is going to have the displacement equal to 0, right? Because it's not going to move. Okay, if the air molecule is exactly at the compression, so the air molecule will not move, because I mean because we're going to have the neighbors molecule that move and then compress to this position. Okay, then we can take that the displacement must be equal to the 0. Okay, also if we look at the air molecules at the rarefaction part here as well, okay, so you can see that the molecules, right, at this position is going to stay at rest as well. Why? Because it's neighboring molecule here, right? It's going to move to the different direction, okay, to compress to this compression region here. Okay, but now if we have the molecules, I mean at the middle of the rarefaction, so it seems that it will not move to, I mean it cannot decide to move to which direction. So that's why the displacement just equal to 0, the same. Now for displacement, right, okay, as I mentioned before, this molecule, okay, this molecule is gonna move to the left hand side, right? Okay, this molecule just gonna move to the left hand side to compress to this part. And also if we consider this molecule, right, these molecules will move to the right hand side and then just to compress to this part. Okay, so it means that, okay, let's consider this one first. The displacement of this one, right, must be negative, and the displacement of this one must be positive. Then the graph should just look something like, okay, the graph should look something like here. Yep, cut off here, right? Because, okay, so here the displacement equal to the 0, and then this molecule, right, in this part, it just moved to the left hand side, the displacement must be negative. Okay, and then okay, and now, okay, the molecule here on this part is going to move to the right hand side, so that's why the displacement must be negative, and etc. So one thing that we can conclude from these two graphs is that, okay, the phase, okay, the phase different between, okay, the change in the air pressure, let me just use the symbol as delta P, okay, the change in the air pressures and the displacements of the air molecules, right, let me just use delta X, okay, is equal to what? Okay, so we have the cosine here and we have the side graph here, so the phase difference is just equal to the 90 degree, and that's it.